Log on, tune in, find out. Another good idea from Cambridge.
At time we tried to mix idea during the coffees, and finally we obtained some results that I will present now. So now for the Schrödinger equation for the linear model, so we have two properties. One is the conservation of the L2 norm, and the second one is the so-called dispersive estimate, which give you a relation between the L1 norm of the initial data and the L infinity norm of the solution at any times t. So the solutions as time evolves decays as t n minus 1/2 in dimension 1. Now, once you have those two estimates, you can prove more general estimates, which are called Strichartz type estimates. We say that if the initial data is in L2, the semigroup will belong to some pair. I think in dimension 1 here it's L4, L4. And this type of estimates, it's used to prove well-posedness for nonlinear Schrödinger equation, for example, with L2 initial data. So the idea is to look to some Schrödinger equations on trees and to try to see if we can obtain such kind of estimates. So we in fact will look to this kind of decay of the solutions. Now about the trees, so here you have a tree. This is a very regular one. So at the time we didn't know the concept, but there is a concept in which is called regular trees, which says that at each generation the edges has the same length, and all the vertices at the same generation have the same number of childs. So here is a nice one. You always have two childs, and here in our case the last generation of edges is made from infinite edges. Okay. Now maybe you like to see the tree in this way. So here what happened, we have some segments here. We have, for example, in this case, let's suppose I have length 1. So you can parameterize each finite edge by 0, 1, and the last one by 0, infinity. And you have to write the system now. And the system is the Schrödinger equation of such structure, or such tree, is just the Schrödinger equations on each segment, which are in 0, 1 in the case of finite 1, and 0, infinity in the case of the infinite edges. Now you have to couple the system. So we assume the continuity of the vortices, and we assume a flux condition, and the name is, I think it's Kirchhoff type condition. So at each node you have continuity. This means that the solution, the U's defined on these three edges has the same value here, and you have also condition of the normal derivatives. And of course you have initial data. Now maybe sometimes it's better to look in this way. So suppose that here is 0, 1, here is 1, 2, here is 2, infinity in our case. And we have here U1, U2. You have to number in the nice way your solution U. So on interval I1, I have U1, U2. Here we have 2 to 1 to 1 to 1 2, and we have the same number here of the same number of as the generation of the tree. Okay. Now you write again the system on the interval 1 2 0 1 1 2 to infinity. You have again to couple. And now, in order to obtain L1, L infinity estimate, we discover that in the case of a regular tree, this type of property is related with some Schrödinger equation on the whole line, but with discontinuous coefficients. Now, just to give an idea of the proof, since the whole proof is not very hard, but it's technical. Just to give an idea, we have to define some averages. And what is important here is that the tree is regular. Okay, so we have, for example, in our case, only power of 2 here. So now we define z1, z2 from 0 to infinity. The second generation we define it from 1 to infinity and so on. And this expression here means the following. So if you look to z1, z1 will be equal with u1 on 0, 1. Here will be the averages of these two, those two, and here will be the average of the four functions here. z22 is equal with u22 on this interval, and in this interval here is the average of these two. Okay, so in principle, this is the idea of introducing the new function z. And once we define in the good way the function z in terms of u, we have to apply a result of Valeria Bănică from 2003, where she considered a Schrödinger equation, but here we have a step function with a finite number of jumps. And she was able to prove that also in this case you have a decay solution as Tn minus 1/2. And now the idea is that in our case, in principle, we can reduce the problem to the case where sigma of x is something like 2 to the power k. Okay, but you have to write carefully the equation. Now, just an idea. So if you have now the z's for the first generation of z's, we have z1 and z2. We make an odd expansion of z1, and we discover that this function z satisfies a Schrödinger equation on the whole on segments with some coupled condition at the integral point. And if you make some change of variables, you reduce the problem to this one here. And for the first for z, we obtain that we use the previous result of Valeria, and we obtain N1 and infinity decay. But since z is equal with u1 and u2 on the first interval, we obtain also that u1 and u2 has a decay property. And after that, we have to make an inductive argument. This means that, for example, assume that we have proved t at minus 1/2 decay for z until the generation k. And we'll go to the generation k plus 1 by just consider for each alpha fixed another beta, which in our case is 0 or 1. Now, you consider the difference between the two on the common interval, whereas both of them are defined, and you have to write carefully the equations. And again, this equation could be reduced to the Valeria case, and we obtain that z tilde alpha beta satisfy such L1 L infinity decay. And using the definition of z and the inductive hypothesis, we can prove that also the generation k plus 1 we have such L1 L infinity decay. Now, some remarks. Those arguments works on regular tree. So if the tree is not regular, we believe that maybe it's true, but we have no idea how to prove it. If you consider graphs, this means that you have a cycle, and maybe the property is not even true, since you can have eigenfunctions on the cycle. And the following idea is to try to analyze such kind of properties for discrete operators. Now, what mean the discrete operators? So I will not work with numerical approximations. So in my case, this discrete Laplacian is nothing else that consider a numerical approximation of the second order derivative and put h equal to 1. And if you consider this equation on the whole, let's say whole line, but is on integral points, we have a decay solution, which is Tn minus 1/3, is not 1/2. Of course, if you put an h here, you can obtain similar estimates. In fact, Stefanov used to put the h equal with 1, and we did something for any h, but in other context. And anyway, so you will have a decay as Tn minus 1/2, Tn minus 1/3. Now, just to give an idea of the proof, is just you can use some Fourier analysis tricks, And you can write the solution U at initial t as a discrete convolution of some kernel which has this form with the initial data. If you look at this convolution, in fact, you have to prove that the kernel decay as t minus 1/3, since and don't care about this one, since the kernel is bounded all the time by 2 pi. Okay. Now, so the idea is try to prove a such estimate here with t minus 1/3, and the idea is to apply van der Corput's lemma. We say that if you have a phase function which has, for example, two derivatives, the second derivative bounded by below by a strictly positive constant, the integral will be less than lambda minus 1/2. If you have the third derivative, you'll have lambda minus 1/3, and so on. And in our case, if you consider this phase function and use the fact that the second derivative and the third derivative never vanish at the same point, you obtain a decay, in our case, as t minus 1/3. Okay, so this is a very simple idea. Now, before to entering the details here, I just want to remember that in the case of the continuous Schrodinger equation, when you analyze Schrodinger equation on trees, you need a result for Schrodinger equation with, let's say, non-constant coefficients. It means that you need some jumps. Okay, and this was the result of Bonica. So our idea is, let's see what's happened in the discrete setting when you have, in the discrete case, we haven't discontinuous coefficient, we have non-constant coefficients. So this means that in the front of the Laplacian, we'll have different numbers. And the idea is try to couple. And the simplest way is to choose, for example, a Schrodinger equation on the negative integers and the positive integers and try to couple. Now, how to couple? One way is to define a common value as 0, that on the left and on the right to have the same values, and to put some flux condition at 0. Now, here the result is easily obtained because you can make some averages, and finally you reduce the problem to the previous one. So I will not enter here in the details, but you'll have also t minus 1/3 decay. Okay, but you have the coefficients here in the front of the Laplacian is 1 and 1. Now, we can observe that our system could be written in this form, in the matrix form. And now here we have something like a diagonal matrix, but we have some changes here in the middle. So the problem is that how to obtain directly, and we have no proof, in the sense that look to the operator A and try to prove that you'll have a L1 L infinity decay of the solution. Just looking at operator is that will make too many computations. Now, and the problem is that A is not a diagonal operator, so we cannot use Fourier transform to obtain some symbol for the operator and to try to use some oscillatory integral tricks. But we can decompose operator. Our operator A is like a classical Laplacian plus a perturbation here. And we think that maybe it's possible to use some properties of the operator B and the decay property for the classical Schrodinger equation to obtain the L1 L infinity estimate for our solution. In fact, our proof is somehow related with some eigenvectors for this small matrix here, but we still don't have very clear how to manage in a general way such idea. Now, what's happened if you have, let's say, discontinuous coefficients? Discontinuous means here that B1 and B2 are different. So since we are in a discrete setting to say that we have discontinuous coefficients. So we have a Schrodinger equation on the left and on the right, but with different coefficients in the front of the Laplacian. We have the continuity as 0 and some flux condition at 0, and we want to analyze this problem. I recall you that in the continuous case, this has been done by Bonica. And if you write the system in the matrix form, now we still have some, let's say, semi-diagonal operator in the sense that above we have diagonals, below we have 3 diagonals, but we have also something in the middle which does not allow us to use Fourier transform and the ideas that you can use in the simplest case when B1 is equal to B2. So now, finally, we obtained a result for this problem. But you need to make a lot of computations since you need an explicit formula for the resolvent. You have to apply Van der Korpel lemma, which we know from before. Some refinements of the Van der Korpel lemma, which has been obtained by Kenning, Pons, and Vega in 2001. Some new lemmas on oscillatory integrals, and a lot of patience since the computations are crazy and you have a lot of constants that you have to control there. Now, just to give an idea, so after a lot of works and forgetting about some terms, you have to estimate such kind of integrals. So for each omega in this interval, you have 2 roots here with modulus less than 1. So you choose only the root which is strictly less than 1. No, you have to choose one of the roots. So in this interval, you have for each omega, you have 2 complex roots, and you have to choose a good one when you write the resolvent. But anyway, the proof is reduced more or less to this estimate here. So we want to have Tn minus 1/3, which we believe that this should be the correct result. Since for B1 equal with B2 equal 1, we know that it's Tn minus 1/3. If you apply directly Van der Korpel lemma, you obtain Tn minus 1/4. We have to make just the second, the third, and the fourth derivative, and to see that they could not vanish simultaneously. But if you want to have Tn minus 1/3, you have to work more. After a change of variable, in principle, you have to prove such kind of result, where here you have a phase function which contains this crazy term, which is arc sinus of a sine of something. And you have to use your software to make formal derivations and to manage your second derivative, the third derivative, to sum there, because by hand I wasn't able to do it. Now, for z equal with 0, these terms disappear, and is exactly the term that appears in the simplest case when B1 is equal with B2 equal with 1. But here, we have to work a lot. And now, I call you again, let's say, a variant of Van der Korpel lemma, but they are more or less the same thing, that allows to put your function phi here. And this is our phase function. We have a parameter a, y, and z, which are here. And we need an estimate to be uniform in z and y, and z and y. Okay? Could depend by a. So sometimes you, in some cases, with this formula here is sufficient, but there are cases where Van der Korpel lemma is not sufficient. Now, the result of Kenning, Pons, and Vega from 91 says that you can accept that the second derivative has zeros. You have to put this here, this weight, and you still have Tn minus 1/3. But also there are cases where this is not sufficient. Now, there are cases where you need to put third derivatives here. And the proof of this lemma is more or less similar with the one before, but you have to be careful because there are cases which are not covered by this lemma. So we need that at the critical point, the first derivative vanishes with some rate, and we will obtain Tn minus 1/3. Now, just an idea of proof. Don't care about all the things here. It's just to say that if z is far from a number, you can apply Van der Korpel without any problem. These numbers appear when you make your computation in Maple software, for example. Now, if b is close to this number, you have to split your interval 0 pi in few parts. The big problem is that pi, so close to pi, you have to split in various intervals, and here appear a problem that you have to see if A is this number or not. So you have in the in one case you have to split in 3 intervals. You have to apply Kenning-Ponsonby-Result, van der Korput with 2 or 3, and in this crazy case for which we spent maybe 4 weeks, 1 month to treat this case, is that you have to split in 4. And now just to show you why it's so difficult to obtain a result for not simple oscillatory integral, because we have trigonometric functions there, is that you have a parameter. Here is b. In fact, b is the difference between which I show you here is this difference here. So if you have a parameter b, you have to and 2 functions q and r. You have Taylor expansion for both of them, but you have a b which could be small, and you have to decide close to pi who of them dominate. Of course, when a is 1 over square root of 2, this term disappears, so you will have neither behavior of q near pi. So you have to be very carefully what's happened close to pi. Now, some things that still remain open is that we don't know. In fact, we tried something, and maybe I'll try next month with Valeria Bănică in Paris to see if we are able to do more on Schrödinger equation on trees. There is another problem to approximate the nonlinear Schrödinger equation with complex Ginzburg-Landau on trees. Also, to give sufficient condition for a matrix A, assuming that A has few diagonals, but not fully diagonal, in the sense that you can have in the middle some terms which does not agree with the whole diagonal, and to obtain the decay of this system, even with the other kind of decay. Now, to couple more than 2 equations, 2 discrete equations, because coupling only 2 allow you to treat discrete equation on trees, but only on a star-shaped tree. And of course, to analyze more discrete equation on tree and graphs, but this is far subject. So thank you for your attention.
For that, there are time for questions. Ari?
You had this matrix, BA or some other thing. And this was a bi-infinite Toeplitz matrix plus a finite dimensional perturbation.
Yeah.
There are results in the literature on such matrices, both the spectral properties and norms and other things. So they are buried in literature as always, but one can find them. I can give you a picture. The other one, there are some new results on the van der Korput lemma, not only of Carlos Koenig, but also of Jim Wright and other people. So this you might find interesting.
New means that few
Last 5 years.
Oh, because I saw something on multidimensional van der Korput lemma or things like that by Jim Wright, but
No? So that's it. Could you give an example where you need to solve a Schrödinger equation on graphs?
so there are some let's say review articles by Kuchman, I think it's from Texas Austin, where he explained quantum graphs and things like that. But to explain you a physical point of view, I'm not able to do it.
Okay, well, thank you for this.